Now, here I have the KPM model for alpha. That the beta one for alpha is just a little bit greater than 1, but it's not significantly different than 1. And this is the alpha or the beta 0 coefficient that represent the market excess return of the alpha. Okay. According to the market efficiency, it is always expected that for all stocks in all time periods, this beta 0 or alpha Jensen alpha in the market model or KPM must be or will not be statistically significantly different than 0. In this case, these alpha returns are statistically greater, or this coefficient or the excess return of alpha is statistically significant, meaning that for this time period alpha has had returns over the market, but this is not expected according to market efficiency. Okay, now if I want to see how, obviously the betas of the KPM are usually calculated using a specific fixed time period, and most of the time financial analysts download these betas from specific sources such as Bloomberg or Economatica. But in this case, you can actually compute your own betas, and also more interestingly, you can see how the market beta of different stocks or portfolios move over time, because the market beta are not static for every stock. They usually change over time. How you can do so? Then what we will be doing is I will be taking like 24 months, run a regression, save the beta, and then use a window with just shifting 1 month down and run the regression and save the beta. And I'm gonna be doing this for windows using 24 months, and I'm gonna be moving the window 1 down. Okay, then this is like, you might be thinking that is like that might be solved with a complicated loop of using 24 rows and moving the time windows every time 1 month down until I finish here, until I finish from the 25 month to the 40 month 49. Then this will be around 24 different regressions for these 24 time windows. But in Stata, I can use something very efficient to program this. That is a prefix of a command that is called rolling. Then in this case, I will be using the rolling prefix before I run a regression. What does that mean is I'm going to be running a regression model, the same KPM model, but I'm going to running that one using the rolling pre command, and I'm indicating here that I'm going to be using a time periods of 24 months, and I'm going to be saving basically the beta of alpha. No, I'm going to be saving the results in this file. This is the name of the file where all the betas, be the beta zeros. When I indicate here is I want the betas to be saved in this file, and this one I also want the standard errors to be saved in this data set. Okay, then when I do this, I have to do a TS set to indicate the data that in this case the month variable is the time variable of the data set. Then when I run these 2 lines, you can see that the month was set as a time variable, and here I run the regression, the rolling regressions, and then 26 regressions were run, and the data was saved in this file. How can I see that data? Then I'm gonna save the data, the current data that I have, that was W8. Then I'm gonna use that now the file that was generated by the rolling regressions, and here you can see I close this one. I Now I open the KPM alpha dataset. Then in this dataset, the actual beta zeros and beta ones of the different regressions using different time windows were stored. Then I can type just edit, and I can see that the regression from December 2009 to November 2011, the beta 1 of the beta of the market for alpha was 0.84, the beta 0 was 0.02, the standard error was of the market of the beta 1 was 0.34, and the standard error of the beta 0 was 0.03. And then every line represents the result of every regression. I have 26 regressions. Then I can see how the beta 1 move over time. I can see that it moves from values of around 0.8, and it moves values of about 1.4, almost 1.5 in this case, and then it went down to 1.3. I can see this better graphically just using the T line. I'm gonna label the variables just to have a better graph. Okay, this is the variable for the beta, and this is the variable for the last month of the regression. This is the variable for the first month of the regression, and I'm gonna set the data set, and then I'm gonna graph it. When I do this, I can see that the beta, this is how beta moves over time, the beta of alpha. There is a very clear graph that is showing me that basically the market risk of alpha has been increasing over time, right? Then there's an interesting trend for alpha. Maybe that is the reason why the beta 0 of alpha usually is significantly different than 0, but also is very risky. Then I can calculate now the t values for every regression to see whether the actual betas are different or equal than 1. Then when I run this one, I am calculating the t values for the hypothesis, for a null hypothesis that the beta is equal to 1, right? And I divide. The way to calculate the t values is the beta minus the hypothetical value divided by the standard error of the variable, in this case of the beta. When I do this, I calculate the t values for all the 26 regressions. Then these are the t values. Then if you see here, what I am looking for are t values greater than 1.96 or greater than 2 to find significance of the hypothesis of the hypothesis testing. I can see that none of the cases there are values over 1.96, meaning that even though the betas have been increasing over time, there is no significance that in the periods these betas are significantly different than 1. Okay, then I'm going to save the file. I'm going to stop here.